In this next part we are going to look at isomorphic graphs. Now, often two graphs may look completely different on paper when you draw them out, but they are essentially the same from the mathematical point of view. They are structurally the same. Now, we got two graphs on the following slide. I'm just going to briefly switch over to the following slide so we can have a quick look. There we have them there. Two isomorphic graphs, and on this side we have this set of graphs. Sorry, this set of edges, and on this side we have this. Okay, whoops. Now the question is, are they structurally the same? Now, these graphs are the same. They have the same vertices, the same edges, and the same edge to endpoint function. Okay. So if we label the vertices on edges on the graph on the next slide by the following mappings, the graphs will be shown to be the same. So we have the vertices here and the edges here. So we're going to show that the edges and the vertices correspond. So first off, let's look at the edges. I'm going to sort of develop correspondence. So I'm going to state that vertex 1 over here corresponds to vertex A over here. And if that is the case, then vertex 3 must correspond to vertex B in that they are adjacent. And they are adjacent by A1. They're adjacent by A1, or on this side E2. Okay. So what I'm saying is that I'm just going to go draw it here. This corresponds to A, this corresponds to B, and this edge here corresponds to E2. Likewise over here we could say that 2 corresponds to C. Necessarily 4 corresponds to D, and we then conclude that A2 corresponds to edge E1. Now, there's a number of ways I could have done that there, but essentially that's how it works. I'm just going to sort of go back to the mapping here for a second. I don't think I've used the exact same mapping here, but it's more or less something like this is what we're trying to construct. So develop correspondence, develop a mapping between the vertices on one graph and the vertices on the other graph, and likewise do the same thing for the edges. Structures, as in graphs, that are the same except for labeling, essentially, are called isomorphic structures. Iso essentially is the same as saying the same as, and morphic means shape, so the same shape. To show that two structures are isomorphic, we must produce a relabeling, as in show the correspondence like we've done there previously, one-to-one onto mappings between the elements of the structures, and then show that the important properties of the structures are preserved under labeling. I'll just give you a quick example of that. Graphs are in graphs, paths and loops and cycles and so on. That's what I mean by properties. Now, in cases of graphs, the elements are edges and vertices. Now, the important property in a graph is which edges connect to which vertices, which edges connect which vertices. And again, you can extend that, as I sort of said, to cycles and paths and stuff like that. So we can use the notation to represent two different graphs, V1E1G1 and V2E2G2, to represent two graphs. The V represents the vertices, the set of vertices. E represents the edges, and G represents the rule linking edges with vertices. So this is an important definition. So two graphs are isomorphic if there are bijections. Remember bijections from functions. So f of 1 mapping from v1 to v2, and an f of 2, which is another mapping e1 to e2. So it's just sort of like the mappings, the correspondence we've done there previously, such that for each edge A, which is for each edge in the set of edges, we can develop a rule for the edges, or for the vertices. That is a sort of supposed to be a arrow. So x is related to y if and only if this set of rules here corresponds to this rule here corresponds to this rule here. It's a very it actually best worked out with going into greater depth with it in an example, but it's a very formal definition. So here, give an example of two isomorphic graphs and list the bijections that establish the isomorphism. So what I'm going to do here is I am going to draw a star graph. It's just a sort of informal name for something like that. And I'm going to label the edges like this: A, B, C, D, and E in the center. And on this side, I'm going to do something similar. I am going to have something here, start up here, and 1, 2, 3, 4. And I'm going to call this U, V, W, X, and Y. Okay. So what we're going to do is try and develop a correspondence. Now, first off, you might notice that E is adjacent to four other vertices. So I'm going to state that E corresponds to U. Okay. Now, we can take our pick with the rest of them because I've done the hard part there. That we can sort of say that V is connected back to U and D is connected back to E. So we can state that let's put D is related to V, and we can do the same for the rest of them. A is related to W, B to X, and Y to C. And we can name the edges there, the corresponding edges, and do the same thing there. So that is a quick example there. It's a very basic example. The examples you'll be dealing with are probably a bit tougher, because it's not always easy to establish if two graphs are isomorphic or not. An exception to this case is the cases where graphs are simple, sort of like what I've just done there a second ago. In this case, we need to check if there is a bijection, a rule that links the vertices of one graph to another, which preserves adjacent vertices, such that if a pairing of vertices are adjacent in one graph, then the corresponding vertices in the other graph are also adjacent, that there's a sort of a similarity there. Now, if the graphs are not simple, we need more sophisticated methods to check if they're isomorphic or not. And however, this is often straightforward to show. It's often straightforward to show that they're not isomorphic. So proof the opposite. And you can do this by showing if any of the following 7 conditions are true. So the first one is the two graphs have different number of vertices. That's almost a giveaway. The second one is the same. They have different number of edges. So automatically, they can't be structurally the same if they have the different number of components. Now, if one graph has parallel edges, for example, something like this, and the other graph doesn't, that's immediately a giveaway as well. If one graph is a simple graph and the other graph is not a simple graph, then so. If one graph has a loop and the other one does not, that's a giveaway as well. If one graph has a vertex of degree k, for example, something like degree 4, and the other does not, if it has the vertex, the highest vertex degree of a vertex is 3, automatically that's a giveaway as well. So you can check a thing called the degree sequence. One graph is connected and the other one is not, and if one graph has a cycle and the other one does not. So those are ways of sort of identifying or stating that two graphs are not adjacent or not isomorphic. And so it's sort of like you try and prove the opposite there. Now you have to be quite exhaustive with it. You have to get if you want to try sort of do this in an exam situation.